Remember that the derivative of e to the x is e to the x. So the integral of e to the x dx will be e to the x plus c. And the integral of e to the u times the derivative of u du will equal e to the u plus c. We use substitution when the power of e is anything other than x. To do this, we let u equal whatever the power is on e, just the power. Then this makes du equal the derivative of the power times dx. We're going to practice finding the indefinite integrals involving e, and our first one is the integral of 7e to the x dx. Remember that when you have a coefficient, you can pull that out in front of the integral sign. So that would be the same as having 7 times the integral of e to the x dx. Well, we keep that coefficient, and the integral of e to the x is e to the x, and don't forget plus c. On our second example, we have the integral of e to the t squared times 2t dt. You would not absolutely have to do substitution on this problem, but just to show you how substitution works, when your power of e is not plain old x, you let u equal that power. So u would be t squared. This means that du equals 2t dt, which is exactly what we have in our problem. So using the substitution technique, we can rewrite our integral as e to the u, and then replace the 2t dt with what it's equal to, du. So it'll be e to the u du. Now we know that that integral just equals e to the u plus c, but we can't leave it with u in it. We have to put back the original power, so it's e to the t squared plus c. On example 3, we have the integral of 900 times e to the 0.3x power dx. First, we're going to let u equal our power, which is 0.3x. This means then du is 0.3 dx. When I look at my problem, I do not have a 0.3 in my problem. I have a 900. So like we learned before when we were doing substitution, when you have a number that doesn't work, it's not what you need, pull it all the way out front. Then we're going to keep our e to the 0.3x. We are going to force in a 0.3 in front of the dx so that we have what we need for du. The problem is we need to offset that by its reciprocal. What you need to remember is that 0.3 is equal to 3/10. So its reciprocal will be 10/3, and that's what we need to offset by out front. So now we have taken our original problem times a1, and it's equal to what we started with, but looks different. If we clean up those two numbers that are out front, we now have 3,000 times the integral of e, and we can take out the 0.3x and replace it with the u, and then du equals 0.3 dx, so we'll have e to the u du. Anytime you get to the point where you just have e to the variable, now you do your integration. So we're going to have 3,000 e to the u plus c. Put back what u was originally, so we'll have 3,000 e to the 0.3x plus c. On example 4, we have the integral of t times e to the negative t squared power dt. It might be helpful if we first rewrite this and put the e in the front and then make it times t dt. Now let your u equal the power of e, which is negative t squared. This then makes du equal to negative 2t dt. And when we look at our problem, we have e to the negative t squared. We only have a 1t dt, so we need to force in negative 2t dt, and then offset the negative 2 with its reciprocal of negative 1/2. Now we are ready to do our substitution. We'll have negative 1/2, the integral of e to the u, and then the negative 2t dt is exactly du, so we're going to replace all of that with just du. Then the integral of e to the u is e to the u plus c. We can't leave it with u in the answer, so we're going to replace u with what it was originally, negative t squared plus c. On example 5, we have the integral of e to the 2x power times the quantity of 1 plus e to the 2x power being raised to the third dx. This is going to be a slightly different type of problem because we have a quantity to a power. So the first thing I'm going to do is reorder this just to help you see it a little bit. I'm going to put the quantity to the power out front and then put the e to the 2x dx at the end. In looking at this now, hopefully what you see is that we have a quantity to a power. So this goes back to being like the problems in the last section. In this case, we're going to let u equal the inside of the quantity. So u will equal 1 plus e to the 2x. This would make du, the derivative of 1 equals 0, and the derivative of the e to the 2x will be e to the 2x times the derivative of the power, which is 2 dx. If you look at our ending part of our original problem, we have e to the 2x times 1 dx. We are going to have to force in the 2. That means we're going to have to offset out front with a 1/2. Our quantity right now is going to stay the same. Then we're going to have our e to the 2x with the forced in 2 dx. We're ready for our substitution. So we will have 1/2 times the integral of u to the third, and then all of the e to the 2x times 2 dx equals du. Now we have a single item to a power, we're going to do our power rule. So we will have u to the 4th over 4 plus c. That gives us 1/8 times u to the 4th plus c, or you can put u to the 4th over 8. Either one is fine. That will give us 1/8 times u was originally 1 plus e to the 2x raised to the 4th plus c. Remember that we learned that the derivative of the natural log of x equals 1 over x. So the integral of 1 over x times dx, which might be written as the integral of dx over x, equals the natural log of the absolute value of x plus c. If you have the integral of u prime over u dx, which could be written as 1 over u du, that will equal the natural log of the absolute value of u plus c. When we are doing these problems and our answer is a natural log, we must put absolute value bars around the argument in the logarithm because the argument must be positive. To know that the problem you are looking at is a natural log problem, the quantity in the denominator must be to the first power. We will again be using substitution in our integrals with natural logarithms. To do the substitution, we're going to let u equal the denominator. This will make du be the derivative of the denominator, dx. You're going to choose to do this anytime your denominator is anything but x. Our first example where we're going to look at this type of a problem is number 6, where we have the integral of 5 over 5x minus 7 dx. First of all, notice that we have a quantity to the first in the denominator. We could think of this as being the integral of 1 over 5x minus 7 times 5 dx. On a problem like this, we have something other than x. We have 5x minus 7 in our denominator. We are going to let u equal that denominator of 5x minus 7. This would make du be 5 dx. So if we substitute into our original problem, we will have the integral of 1 over u, and the 5 dx gets replaced with du. Now that I have the integral of 1 over u, I know that's a natural log for the answer. So my answer will be the natural log, the absolute value of u, plus c. Remember, those bars have to be there, and that's to show that that argument has to be positive. We take out the u and replace it with what it was originally, 5x minus 7 plus c. On example 7, we have the integral of 2x over 1 plus x squared times dx. Recognize that this could be rewritten as the integral of 1 over 1 plus x squared times 2x dx. This is how we know that it's a natural log problem, when you could rewrite it as 1 over a quantity. So we are going to let u equal that quantity to the first, the 1 plus x squared. This would make du be 2x dx. Substituting into our integral, we will have the integral of 1 over u du, which is the natural log of the absolute value of u plus c. Replace your u with what it was originally, so we have the natural log of 1 plus x squared plus c. On example 8, we have the integral of 1 over 5x plus 4 dx. This one's already in the 1 over quantity format, so we can jump straight to letting u equal that quantity to the first, 5x plus 4, which makes du be 5 dx. In our problem, we don't have 5 dx. So we're going to force that in. The fraction's going to stay the same, 1 over the 5x plus 4. We're going to make it times 5 dx, forcing in the 5, which we have to offset with its reciprocal, 1/5. Now we have what we need for substitution. Keep your 1/5. You'll have the integral of 1 over u, and the 5 dx is exactly du. So keep your 1/5. The integral of 1 over u is the natural log of the absolute value of u, plus c. Take the u out and put what it was originally, so we'll have 1/5 the natural log of 5x plus 4 plus c. On number 9, we have the integral of 8x cubed over 3x to the 4th plus 7, and all of that's times dx. It might help you if you always start out by writing your fraction as 1 over the denominator, and then make it times the numerator, 8x cubed dx. This can help you see what your u and du are more distinctly. In this problem, we're going to let u equal 3x to the 4th plus 7, which gives us a du of 12x cubed dx. And when we look at our problem, we don't have a 12 with our x cubed dx. We have an 8. So that item that we don't want there, that 8, we're going to pull it all the way out front, just like we learned before. We're going to leave our fraction alone as 1 over 3x to the 4th plus 7. And then we're going to force in the number that we want, a 12x cubed dx, which means we have to offset out front with 1/12, the reciprocal. 8 over 12 simplifies to be 2/3 the integral of 1 over u, and the 12x cubed dx is du. We're going to keep our coefficient of 2/3. The integral of 1 over u is the natural log of the absolute value of u plus c. Replace the u with what it was originally, so you have 2/3 natural log the absolute value of 3x to the 4th plus 7 plus c. On number 10, we have the integral of x squared plus 1 over 2x cubed plus 6x. All of this is times dx. Let's rewrite it as the 1 over. We will have the integral of 1 over 2x cubed plus 6x times x squared plus 1, and that's a quantity, so I'm going to put it in a set of parentheses, times dx. In this case, our u will be our denominator of 2x cubed plus 6x, which would give us a du of 6x squared plus 6 dx. The problem is that in our original problem, we have an x squared plus 1, not 6x squared plus 6. What you need to notice is you can factor out a 6, and then that would become x squared plus 1 in the quantity dx. So we need to force a 6 into our problem, which means we are going to offset it with a 1/6 out front, the integral of 1 over 2x cubed plus 6x times 6 times the quantity of x squared plus 1 dx. Now everything matches the way we need it to. We're going to carry our 1/6 along and do our substitution. We will have the integral of 1 over u, and the 6 times the quantity times dx is all du. Keep your coefficient of 1/6. The integral of 1 over u is the natural log of the absolute value of u plus c. Take out u and put in your x quantity, so we'll have the natural log of the absolute value of 2x cubed plus 6x plus c.